let's put it all together here. So calcium hydroxide reacts with silver nitrate to produce calcium nitrate and silver hydroxide. If you start with 10.00 grams of calcium hydroxide, how many grams of silver hydroxide will be produced? Okay, so let's start out first things first. We got to write the reaction. So calcium hydroxide reacts with silver nitrate. So what's calcium hydroxide's formula? Ca parentheses OH 2. Right, calcium's 2 plus, it's in group 2. Hydroxide is 1 negative, you had to memorize that. Okay. Reacts with, so plus, silver nitrate. So find silver on your periodic table. It's Ag, and it's a charge of what? 1 plus. Nitrate's 1 you had to learn. It's NO3, 1 minus. So what's silver nitrate's formula? Ag NO3. Those react to produce, I'm going to put a little arrow in here, calcium nitrate and silver hydroxide. What's calcium nitrate? What's calcium nitrate? Ca. Nope, parenthesis. NO3. How many do I need? 2 of them. Calcium's 2 plus, nitrate's 1 minus. Plus, what would silver hydroxide be? Ag. What's the charge on silver? 1 plus. What's the charge on hydroxide? 1 minus. So just 1 of each. AgOH. Okay, now, but it's not balanced, so let's balance it. So look at that. How would I balance this out? Calciums, balanced hydroxides, balanced silvers, balanced nitrates. Let's figure this out here. Yeah, question. No. Oh, answer. Okay, yeah, sure. Yeah, sure, tell me. Yeah, what is it?
Would you put a 2 in front of silver nitrate and silver hydroxide?
Okay, what do you think? Does that do it? Let's see. 1 calcium on the left, 1 calcium on the right. 2 hydroxides on the left, 2 hydroxides on the right. 2 hydroxides, 2 hydroxides, 2 silvers, 2 silvers, 2 nitrates, 2 nitrates. Yes, so that balanced it. Perfect. Good job. Okay. 10.00 grams of, what is it? Okay, calcium hydroxide. If you start with that many grams of calcium hydroxide, how many grams of silver hydroxide will you produce? Okay, so I see lots of word clues in there. I see grams. That means I'm going to have to use molar mass. I want to go to grams. I'm going to have to use molar mass again. But it's 2 different things. One of them is calcium hydroxide. One of them is silver hydroxide. So 2 different things. I got to use the mole ratio. So what I want to do first? Well, first thing I've got grams of calcium hydroxide. So what's the only thing I can do with mass? Molar mass. So what's the molar mass of calcium hydroxide? So add up a calcium, add up 2 oxygens, add up 2 hydrogens. So 40 and 32 and 2 is 34. I think it's 74.10. What did you get for the molar mass? What is it?
74.
Okay, good. Okay, so now I'm in moles of calcium hydroxide, but I have to relate calcium hydroxide to silver hydroxide. So I do that out of my balanced equation. So how do I relate calcium hydroxide to silver hydroxide? Yeah, mole ratio, which is what is it? What is it? What's the relationship? For every 1 calcium hydroxide, I make 2 silver hydroxides, right? So I'm going to put the calcium hydroxide on the bottom, 1 calcium hydroxide to 2 silver hydroxides. Okay, moles calcium hydroxide cancels. Now I'm in moles of silver hydroxide, but I want to be in grams. Moles to grams, molar mass again, right? So just add up a silver, an oxygen, a hydrogen, see what you get. One 24.88, something like that. Anybody do it? Is that right? Okay. 124.88 grams is a mole of silver hydroxide. So now moles of silver hydroxide cancels. Okay, so let's punch that in our calculators. Punch it all in there. 10 divided by this times 2 times 2, whatever. How many sig figs should I have? 4. Yes. So what is it? What? 33.71? 33.71 grams. Awesome. Okay, kind of see how this all comes together, right? The naming, the equations, the balancing, everything, it all ties together. So this is, okay, why don't you try this one? I think your handout's wrong, by the way. By the way, so I think yours is, my A is your B, I think, or something like that. Because yours is already, yours says the balance and it's already balanced. So just jump down, is that right? Yes, just jump down and try B then, which is what I have as A. So try it out. I already gave you the balance equation this time. If you have 0.15 kilograms of iron 3 oxide, how many grams of CO will you need? So 2 different things, 2 different masses, so you kind of know what to do here. Try it out, help each other out. Talk, talk, talk. Point 150 kilograms of iron 3 oxide. So 0.150 kilograms iron 3 oxide. Okay, what do I gotta do first? Convert kilograms to grams. 1 kilogram, 10 to the third grams. Okay, now I'm in grams of iron 3 oxide. So what do I do with grams? Molar mass. What's the molar mass of that? 159. What'd you say? 70. I'm sure you meant 70. That's the mass of a mole of Fe2O3. I'm in Fe2O3, but I want to be in CO. So that's where I use this mole to mole ratio. Moles Fe2O3 compared to moles CO. According to the equation that's balanced, it says it's 3 COs to every 1 Fe2O3. Now I'm in moles of CO, but I want to be in grams of CO, so molar mass. 12 and 16, 28.01 grams.
I have a question.
Yes.
I got 3, but I won't base that to 3 on the other side of the equation. Are we
The
supposed
CO2? But it's CO. It's CO. That's CO2. Okay, so what'd you get now? What?
78.9.
78.9? Everybody seem to get that? Okay, good. By George, I think we're getting it. Okay, just practice. Just practice. Any questions on that? So I promise it's just kind of the same thing. Always molar mass or mole ratio or Avogadro. Just one of those 3 things. Just knowing when to use which one. Okay, let's try another one. Calculate how much iron would you get from that, and how much CO2 would you get from that. So the first part's all the same. The only part that changes is the little last bit, so I'm not going to work it all out. But the first part was all the same. So now it's saying relate this to the iron, and then relate it to the CO2. So let's just do it to the iron. Oops, sorry. 1 kilogram, 10 to the 3rd grams. And then we got, what was the molar mass of Fe2O3? 159.7. I'm sure you meant to say 0. Is a mole of Fe2O3. But now we're going to find iron. So for every 1 mole of Fe2O3, our balance equation tells us there's how many irons? 2 moles of iron, right? And then we just do molar mass of iron. So 1 mole of iron, I think it's 55.85. So whatever that answer is. Anybody? Punch it in there? Yeah. Anybody? No? Just give me a number. It's okay to be wrong.
104.91.
104.91. Anybody else? Okay. How about to find the CO2? Well, this would all be the same. It would only change right here, right? Now I would relate Fe2O3 to 3 moles of CO2.
Isn't it 104.9?
Oh, it's,
Wait, no, there's
oh no, wait, it's 3 sig figs. It's 3 sig figs. You're absolutely right. 105. 105. So now it's CO2, so same thing, but molar mass of CO2, 32 and 12, 44.01 grams per mole of CO2, then whatever that gives. So the first part's all the same, right? All you're changing is waiting to iron 3 oxide to CO, or iron 3 oxide to iron, or iron 3 oxide to CO2. Doesn't matter. All the changes is that last little step there. Okay, so that's how we do it. So we can, so like I said, this is super handy if you're in the lab or whatever, or on the job and you want to know, okay, I want to make this much iron. How much iron 3 oxide should I put in to make that much iron? Or I want to make this much of a new drug. How much of these reactants should I use? Again, and you do all this math, and then you know exactly how much to use. So you're not wasting chemicals, just add, I'll just try a little of this, try a little of that, then you don't have enough, or you have too much, you just wasted time or chemicals. So now we can calculate, if I want to make that much iron, I got to use that much of Fe2O3, so you know how much you're going to need, or you know how much you're going to make. Okay, however, you may not always have the exact stoichiometric 1-to-3 ratio. So I'll give you an example here of building a car. So let's just assume that cars are really easy to build, and it was literally just car bodies plus 4 wheels makes a car. So for every 1 car body, I could put on 4 wheels and I get out 1 car. So it's a 1-to-4-to-1 ratio, right? In that example. Okay, so let's say you go to the car factory, and the question is, does that work for mass? Could I have a ratio of, let's say, 1 pound of car body to 4 pounds of tires to get out, right? Well, does it work for mass? Could I say a pound of car plus 4 pounds of wheels gives 1 pound of car at the end? Of course not, right? Again, it doesn't work for mass, it only works for pieces, which is why we're using molecules and moles and things like that. So it doesn't work for mass. So what if I don't have what if I don't have 1-to-4-to-1? Let's say I happen to have a line around the car factory, 3 car bodies and 16 wheels. How many cars can I make?
3.
Okay, I want you to remember how easy that was for you. It's just that easy for the chemistry, I promise you. But you get into your head, it's, oh my God, it must be harder. But it's not. So every car took 4 wheels, right? Just like earlier on a reaction. Every iron 3 oxide took 3 COs, right? Just 1-to-3. Now it's 1-to-4. So this one takes 4. This one takes 4. This one takes 4. Exactly. So I can make 3 cars. Okay. So which reactant do I have an excess of? Which reactant did I have more than I needed, in other words? I had lots of wheels, right? I had an extra 4 wheels. Okay, so the 2 reactants, I had more wheels than I needed. That's called the excess reactant. Okay? So which reactant did I run out of that actually limited my car production to only 3 cars? I ran out of the car bodies, right? Okay. So the one that limited me to only making 3 cars, that's called the limiting reactant. So, whenever you have, so again, we didn't have the exact 1-to-4 ratio we needed, so therefore one of them we had a little too much of, that's the excess reactant, and one of them ran out and limited us, so it's called the limiting reactant. So, I had enough wheels to make 4 cars, right? But I only had enough car bodies to make 3 cars, so of course I can only make whatever the smaller is, 3 cars. Okay, so the reaction, I'll say it again because you're not writing anything down, I don't know why, but the reaction that ran out and limited me, that's called the limiting reactant, right? The one that ran out, because it limits how much product I can make. So whatever reactant is completely consumed, completely used up, in our case it was car bodies, we used up all the car bodies. So car bodies was the limiting reactant because it limited me to only 3 cars. All of the other reactants that I had more than I needed of, those are going to be the excess reactants. They have more than I need. I have an excess of them. So let's get like tires or wheels, right? I had more than enough wheels. Okay, so let's go back to chemistry. And exact same thing. The ratio for chemistry is, for every 2 hydrogens, I need 1 oxygen to make 2 waters, right? Same thing. So, what if I put in 6 hydrogens and I put in 4 oxygens? How much water would I make? So, we're going to figure it up. So, we're going to see, okay, 6 hydrogens, how much water could that make? 4 oxygens, how much water could that make? So let's just try it out. So for every 2 hydrogens, I can make 2 waters, right? right? So that means I could make how many waters altogether? 6 times 2 divided by 2? 6. Okay. How about 4 oxygens? Well, for every 1 oxygen, I can make 2 waters, right? So how many waters could I make? 8. So, I'll let you finish writing that down, then I'll talk about it. Okay, so before I had 3 car bodies, I could make 3 cars. I had 16 wheels, I could make 4 cars, but I had to pick the one that was only 3 because that's the one that ran out first. So the question is, will I make 6 moles of water or will I make 8 moles of water? No. Why will I not make 8? Because what happens? Because the hydrogen runs out after I make 6. There's plenty of oxygen to keep going to make 8, but this one runs out and limits me to only making 6, right? So there's enough hydrogen to make 6 moles, there's enough oxygen to make 8 moles. So what do I actually make? The smaller one. You always pick the smaller one. Okay, so the limiting reactant is the one that produces the least amount, the smallest amount. So in that case, what's my limiting reactant? Well, hydrogen is my limiting reactant, right? Because hydrogen limited me to only making 6 moles of water, right? But I had plenty of extra oxygen. The oxygen was ready to keep going and make 7 moles, 8 moles, right? There's plenty of oxygen. So oxygen's the what? What's it called? Excess reactant, right? Okay. That makes sense. So I know the wacky part, people would think, oh, well, 4 is less than 6, but you can't look at this. You got to look at how much you actually make at the end, right? So 6 is less than 8, so 6 is what I'm going to make because this runs out first. Okay? Okay. Good. So let's try one together here. How much molten iron, Fe, would I make from 25.0 grams of this and 25.0 grams of this? Okay. Now you would think at first, oh, well, they're exactly equal. But again, that math doesn't matter because it's all about the particles, the pieces. So we're going to do the same thing we were just doing. We're going to do it twice. I'm going to turn 25.0 grams of iron 2 oxide into iron and 25.0 grams of aluminum into iron. And then we're going to pick which one. Which one's the winner? Which one's the winner of the 2? The smaller one, right? The smaller one's the winner, right? The smaller one is going to be the amount we actually make. Okay, let's try this here. So 25.0 grams of iron 2 oxide. What's the first thing I do? What's the first thing I do?
Convert to moles.
Convert to moles, yes. How do I turn mass into moles? Have you learned nothing? I guess I use molar mass, right? Molar mass, grams on bottom, moles on top. So iron and oxygen, 55 and 16 is what, 71.85? I think that's right. Isn't iron 55.85? Yes, okay. That's the mass of a mole of FeO. So again, I'm just doing 2 things. I'm going to turn iron 2 oxide into iron, and then I'm going to turn aluminum into iron. Just like I did last time. I turned car bodies into cars. I turned wheels into cars. I picked the smaller one. Same thing here. Okay. Now I'm in moles of Fe2O, but I want to be in iron. So how do I relate FeO to Fe? The ratio. So, yes. So for every 3 moles of Fe, I need 3 moles of FeO, right? Right? Okay, well, I have moles of iron, but I want, well, it doesn't really say it says how much, so that's amount, mass of iron. So how do I do that? Molar mass. So find the molar mass of iron. It's 55.85 grams is a mole of iron, according to your periodic table. Okay, so you punch that all in there, and let's see what the first one gives me. So what's the first one give me? Oh, I think I actually did it. I guess I can look. I did, okay. 19.4 grams of iron for the first one. That's what I got. Okay, so that's the first one. So now I've taken iron 2 oxide and turned it into iron. Okay, now let's try the other one. Let's try aluminum and turn it into iron. All right, so we're going to do this one. Aluminum into iron. So same thing, I had 25.0 grams of that too. So what's the first step if I have mass of aluminum? What do I do? Molar mass. So what's the molar mass of aluminum? Okay, 26.98 grams of aluminum per mole of aluminum. It's the molar mass. How do I, now I'm in aluminum, but I want to be in iron, so what's the relationship between aluminum and iron? 2 aluminums makes 3 irons. 2 moles of aluminum makes 3 moles of iron. Now I have moles of iron, but I want, again, mass of iron. So moles to mass, we use molar mass again. So let's see what I got. I got 77.6 when I did it. Okay, so let's summarize what we got. The 25.0 grams of iron 2 oxide could produce 19.4 grams of iron. The 25.0 grams of aluminum could make 77.6 grams of iron. How much iron will I actually make?
19.
The smaller one, right? I'm going to make the smaller one. Why is that? Why don't I make 77.6? Because why? Yes, because, well, I don't have enough iron oxide, right? Because this runs out after you make 19.4, right? So there's plenty of aluminum to keep on going, right? It'll keep going like crazy, but I run out of this when I hit 19.4. So yes, so I'm going to make 19.4, which means which of those reactants is the limiting reactant? Iron 2 oxide, FeO, right? Which means the aluminum must be the, yes, there was plenty of aluminum, right? Plenty of aluminum to keep on going, right? Make another almost 60 grams. Make sense? No? Okay, let's try another one. Okay, this is a similar one, but now it's not iron 2 oxide, it's iron 3 oxide, but similar kind of reaction. There's a reaction called the thermite reaction. You might have heard this before. It's a very hot reaction again, and it makes liquid iron. It makes lava, basically. It makes molten iron. And these are like a railroad. railroads so they can weld steel rails together. If you ever watch Breaking Bad, they used it one time Breaking Bad to burn open a lock on a building. They used a thermite reaction. So it's kind of cool because you take aluminum powder, which is just a powder, iron oxide is still powder, mix it together, a little spark, becomes thousands of degrees hot and makes lava out of just these two room temperature powders. So it's a crazy big reaction. So everybody have that reaction written down or your hand out there, right? Okay, good. So let's look here. Suppose I mix 113 grams of aluminum with 279 grams of this. What mass of iron could I make? So let's look here. So I have, right now what I know, 113 grams of this and 279 grams of this. And I want to know how many grams of this could I make, right? So the way to figure it out is to do two reactions. I'm going to turn aluminum into iron. I'm going to turn iron 3 oxide into iron. And then I'm going to pick which one is the winner. Out of the two possible answers I get, how do I know which one's the right answer? The smaller one, the one that's less, or the one that makes less, right? The smaller one. Okay, so let's try it here. So, doesn't matter which one you do first. I guess I'll do the aluminum first, because it's written first. Doesn't matter though. So 113 grams of aluminum. What's the first thing I'll do with mass of aluminum? Molar mass. So molar mass of aluminum is 26.98 grams is a mole of aluminum. What will I do next? I've got moles of aluminum. Do the ratio. Compare the aluminum to the iron. So what is that ratio?
2 aluminum for 2 iron.
2 moles of aluminum on bottom makes me 2 moles of iron on top. Right, good. Now I've got moles of iron, but I want mass of iron, so what do? Molar mass again. So find iron on your periodic table. 55.85 grams is a mole of iron. So punch that all in your calculator. Somebody tell me what you got. It's going to be 3 sig figs, it looks like. $234? Okay, great. 234 grams of iron. Okay, now let's just try the other one. Now let's see, how about that iron 3 oxide? Well, 279 grams iron 3 oxide. What's the first thing I have to do?
Mass.
You have the mass, I'm going to use the molar mass. So we add up 2 irons, 3 oxygens. I did that earlier for something, seems like. 110 and 48, 150. 9.70, something like that. Okay, now what? Now I've got moles of iron 3 oxide. What's next? The ratio, mole to mole ratio. So for every, how many iron 3 oxides? Now it's 1, according to the ratio. I make 2 irons. And then the rest is the same. Moles of iron turn to mass of iron. I use molar mass again. So somebody punch that in. 3 sig figs again.
195.
195. Okay, so we got 2 possible winners. So if I mix those, how much iron would I actually make? What's
185.
I would pick the smaller, right? Right? I picked the smaller. Okay, so that means which of the reactants was the limiting reactant? The one that limited me to making it. So yes, this right here. This was my limiting reactant. I'll put LR. So Fe2O3 was the one that limited me to making the smaller amount. Which reactant was there more than enough of? Which one was the excess reactant? Aluminum was the excess reactant, right? Okay. Good. Okay. Do I have another one here? I do, okay. Okay. Acrylonitrile, C3H3N, is the starting material to make acrylics. You know, it's an artificial fabric. If I have an acrylic sweater or something in your house. And can be made from propylene by reaction with nitrogen monoxide, or the old school name is nitric oxide. Like this. So here's the reaction. So, what mass of this could I make? So let me just start writing here. So the question is, how many grams of this, question mark grams, if I have 21.6 grams of this and 21.6 grams of this? Okay. So what do I have to do here? What's my path? What am I going to do? Start telling me things. I don't care. What do you think I'm going to do?
Pick which one you want to start.
Do what? Pick what?
Pick which one you start.
Okay. So just pick one, right? So let's do C3H6 first. Okay, great. And then what do I want to do with that C3H6? Yeah, I want to take it and I want to turn it all the way into C3H3N, right? That's my goal. Then we'll do the same thing for the NO and turn it into C3H3N, right? Okay. So 21.6 grams of propylene. So yes, somebody said molar mass first. So 3 carbons and 6, 3 times 12 is 36, plus 6 is 42.09 grams is a mole of propylene. What do I do next? Yeah, I want to relate propylene to this stuff, acrylonitrile. So it tells me for every 4 propylene, I make 4 acrylonitriles, right? Okay. But I want to know mass of acrylonitrile, so what do I do next? Okay. So 3 carbons, 36 plus 3 more is 39, plus 14 is 53.07, something like that. That's the mass of a mole of C3H3N. So punch that in your calculators. I don't have mine. I won't do it, but tell me what you get. $27.2 grams, okay. Okay. We're halfway there. What do I do next?
Make another.
I'm sorry, what?
Make the other.
Yeah, make the other ones. Let's take 21.6 grams now of NO and turn it into acrylonitrile. So molar mass first. So a 14 and 16 makes 30.01. How do I relate moles of NO to C3H3N? One more ratio, which is what now? What is it though?
6
6 NOs
equals 4.
to 4 C3H3Ns, right? So 6 moles of NO to 4 moles C3H3N. I've got moles, we've got to use molar mass. We already found that last time. It's the same molar mass, 53.07. So we punch that one in. Let's see what we get. $25.5. Okay. So the question is, how much will I make? The smaller of the two, right? You always pick the smaller. You pick the smaller. So, based on that, which of those was the limiting reactant? Yes, this was my limiting reactant. What was the excess reactant? C3H6, right. Okay, got 5 minutes here. No, wait. Yeah, that's right. Right. Okay. Any questions on that one? Okay. So now when you're actually in the lab though, of course, so what I just showed you was the amount you would make if everything went perfectly, right? You'd make 25.5 grams. But of course in the lab, you know, things happen, you spill stuff, you burn stuff, you heat it too long, or whatever. Things happen. And you may not actually make that. The amount you actually make, we call the actual yield, which may not be 25.5, let's say. Okay? But the amount that you calculated you should have made, that's we call the theoretical yield. So theoretical yield is the one we just spent all that time figuring up. So that's how much we should make if everything goes flawlessly. So the percent yield then is a comparison to, well, what percentage of this ideal amount did you actually get? So you just take the actual yield, the amount you actually made, divide it by the theoretical yield, the amount you should have made, and multiply it by 100. So maybe you'll get, oh, I only got 94% of what I should have, or I got 73% or what I should have. So that's called the actual yield. So, where's the theoretical yield come from? Where's it come from? You have to calculate that one, right? The actual yield, well, you have to go in the lab, run the experiment, and actually find the, you have to actually do it. So you have to be given that one. So you have to be given a problem that would say, oh, the reaction was run and you produced this much. Well, that would be how much you actually produced. Okay, so let me see if I can squeeze this one in real quick here. Oh yes, a different count on this one. So let's say it says a student performs a reaction and they got 0.875 grams of copper 2 carbonate. But the theoretical yield, so about the calculator they should have got was 0.988 grams. What would the percent yield be? So, percent yield is actual over theoretical times 100. So actual 0.875 over theoretical, oh, I should have made 0.988 times 100. So what was my percent yield? How did I do? Obviously, the closer to 100%, the better. So what is it? 88.6%. Pardon me? 88.6%. 88.6% is my yield. So again, this one is always calculated. This one you have to find it in the lab. So normally the problem is given to you. Or in the lab will do it and we'll watch you just measure it out, figure out how much you made. Awesome. Okay, I don't think we're gonna have time. We're so close. So tell you what, let's finish it Monday. Let's push the test back to Wednesday, I guess. My only hesitation to say that is I fear that a bunch of you will mean, yeah, they can wait to study on Monday, but please don't. So now you have an extra 2 days. So start studying now, right? Come see me, ask me questions. So we'll finish chapter 6, and then we'll also start 7. So bring your 7 PowerPoint. We'll have the test like on Wednesday. Yes.
Is the homework still due on Monday then?
No, I'll push it back till Wednesday
It says
then.
on Monday.
Yes, so I will push it back till Wednesday now that I'm changing that. But I'm telling you, that does not mean wait till Monday to do the homework, right? Because you will be out of luck. So start practicing it.
Wait, so
Ask me questions. Go to FLS. Come see me, Tutorial Center. Yes.